Hello. Welcome to this short video estimating the dark matter mass of our Milky Way galaxy. We will use two speeds and two distances from astronomy to estimate the total mass of the Milky Way galaxy and to guesstimate how much of that mass is dark matter. Our purpose is to get approximate estimates from simplifying assumptions, simple physics formulas, and a few measured values from astronomy. I took values from Wikipedia articles without checking against authoritative references. The Sun has a slightly elliptical orbit around the center of the Milky Way galaxy, but let's assume a circular orbit with radius, lowercase r, of 26,000 light-years. Astronomers say that our orbital velocity, lowercase v, is 250 kilometers per second. Let's treat the total gravitating mass of our galaxy as spherically distributed, even though the Milky Way is a spiral galaxy, not an elliptical galaxy. Let's equate the centripetal acceleration with the gravitational acceleration using lowercase m as the gravitating mass within our orbit. So v squared over r is the centripetal acceleration. Gm over r squared is the gravitational acceleration, and capital G is Newton's gravitational constant. Let's rearrange to give the mass within our orbit. Mass equals v squared r over g. Let's substitute values, and we get 0.117 trillion solar masses inside our orbit. Now, astronomers know the radial velocity of the Andromeda galaxy toward Earth from the blue shift of light emitted from Andromeda and received at Earth. 300 kilometers per second. I assume this is averaged over our year. Astronomers say that the radial velocity between the centers of the Andromeda and Milky Way galaxies is 110 kilometers per second. If the masses are equal, the velocity of each toward their common center of mass is half of this value, 55 kilometers per second. Astronomers do not know the non-radial tangential proper velocity, which we will assume is zero, such that the motion is entirely radial. Astronomers know the distance between the Milky Way galaxy and the Andromeda galaxy from Cepheid and RR Lyrae variable stars, 2.5 million light-years. Dividing the distance by the present speed, the two galaxies should collide in less than 6.8 billion years. We'll do a better calculation at the end of this video. The masses of the two galaxies are not known precisely, but they seem comparable to one another. Let's assume that the masses of the two galaxies are equal. This will be fine for our estimates. Let capital M represent the total mass, dark matter, stellar mass, gas, and black holes of each galaxy plus its gravitationally bound satellite dwarf galaxies. The potential energy, capital U, of their mutual gravitational attraction is U equals minus GMM over R. Assuming the two galaxies have the same mass, they are each moving toward their common center of mass at the same speed, capital V over 2. The total translational kinetic energy, capital T, is twice 1/2 mass times velocity squared, but in this case the velocity is V over 2. So we get 1/4 mv squared. Assume the total energy is zero and ignore rotational energy. Total energy is kinetic energy plus potential energy, so 1/4 mv squared minus GMM over R. We solve for the mass, capital M equal V squared R over 4G. We substitute values, and we get 1/2 trillion solar masses, including satellite dwarf galaxies. This is about 2 to 3 times too low, but that's fine for our assumptions and estimation purposes. Now, we divide the mass within our orbit by the total mass of the galaxy. So lowercase m divided by uppercase m. And we get about 22%. 22% of the mass of the galaxy is within the Sun's orbit. The cores and bulges of the Milky Way and Andromeda spiral galaxies are impressive for their numbers of stars, but most of the galactic mass is beyond the Sun's orbit. Let's guesstimate that most of the mass within our orbit is stellar mass, gas, and black holes, not dark matter, and that almost all of the mass outside our orbit is dark matter. Then, dark matter would constitute about 80% of the mass of the Milky Way galaxy. Astronomers believe the number is around 90%. If we attribute half of the mass within our orbit to dark matter, we would get 90% for the dark matter fraction of galactic mass. This is good enough for our assumptions and guesstimates. Now let's do a better calculation of when Andromeda and the Milky Way will collide. If no errors on my part, this formula would be the time in the future when the centers of the galaxies would collide, assuming all the mass is at the centers and the motion is only radial. Time equals 1/3 square root of capital R cubed over G capital M. Now we substitute values, and we get 4.5 billion years from now. Astronomers say Andromeda will collide with the Milky Way between 2.5 and 4 billion years from now. I hope this video has been useful to you.